Hello again, everyone. We are going to wrap up lesson 3.1 in this video by talking about complementary events and probability applications. We've got a short one for you today, so let's go ahead and dive right in. Complementary events. So two events that complement each other together encompass the entire sample space of an event. Let me show you what I mean by saying that. So, the first thing we need to establish is that the sum of probabilities of all outcomes in a sample space, the sum of the probabilities of all the outcomes in a sample space altogether is 1. Okay, we could also say 100% if you like thinking in terms of percentages, but if you add all of the probabilities together, we get a grand total of 100%. Okay. The complement of an event E is the set of all outcomes in the sample space that are not included in E. So let me show you what I mean by that. So in an example, what is the probability that an employee chosen at random will not be 65 or older? Well, the first thing we would want to do here with this data set is figure out what our total is, right? So we've got 6 numbers all together, and they're labeled frequencies. So I'm going to use some notation from back in chapter 2. The sum of all these frequencies all together here ends up being 1,000. So we have 1,000 employees, and we can see very plainly right here that 42 of them are over the age of 64, or 65 rather. 42 of them are over the age of 64. So if I answer the question, what is the probability of being older than, let's see how they word this here, 65 and over. We'll use their language here. Probability of being 65 and older. We would say, well, there are 42 people out of 1,000, which is 0.042, 42 thousandths. Great, but the question they were asking us to answer is the complement of this, or think of it as the opposite. Find the probability that an employee chosen at random will not be 65 years or older. So the probability of not 65 and older. Well, that's going to be literally everyone who is not 65. I'm not even going to write that because it's just saying the same thing. It's everybody who is not 65 and older. So we know 42 people are 65 and older. So that's going to be the other 958 people. If my math is right, that should add up to 1,000, right? 958, which from a probability standpoint must be 0.9. Let's see here, 958, obviously. So what's true about these two events here? Well, they together encompass the entire sample space. You're either 65 and older or you're not. So we would say that these two events here, these are complementary events. Because together they add up to 1 from a probability standpoint, and we can tell that they are complete opposites of each other in terms of what portion of the sample space they are addressing. just to drive this point, just to finish this out so it's nice and pretty here, our blue not 65, and then our green would be 65 and older. And altogether that adds up to 1. So there's some notation here that's often used. So complementary events are often notated like this. So if we have, I'm trying to think of the easiest way to say this. So in terms of an event, so the probability of some event E, we would say that the complement of that event can be written the probability of E prime. So that's one more thing that we should mention here, is that this E prime is notation for the complement of E. Okay, so another way that we could have said the blue piece here, not 65 and older, is we could have said find the probability of, we could just shorthand this, greater than or equal to 65. That means, 65 and older, right? Prime. So it's kind of goofy applying the prime business to kind of like that shorthand explanation in the parentheses of what the probability question is asking. But the point here is that, so when we see this, it means, this means we are looking for the complement of this. So I'll put an equal sign there. So the complement of being greater than or equal to 65 is being less than 65 or not 65 and older. So that would be another way of saying that, using that notation with the prime to mean, hey, we want the opposite of what is being stated here. Okay. Applications here. So let's say that we have a college ID that consists of 8 digits. As always, I like 1, 2, 3, 4, 5, 6, 7, 8. Drawing out my 8 lines here. The first 2 digits must be your enrollment year. So we don't have any choices, no choices for those first 2 digits there. The first 2 digits are locked in. Okay. The college is choosing one ID number at random to win a scholarship. Find the probability of randomly generating your ID number. Wow. Okay. Okay, so the question here is, how many possible ID numbers are there? And that's what we started to build here. So there's a couple assumptions we have to make here. The first assumption is they didn't mention anything about repeating digits. So when they don't mention that, we assume that repeats are allowed. Assume they're allowed unless told otherwise. So we know that for the remaining digits here, we've got lots of choices, 10 choices for each digit place after those first 2. It can be any numbers between 0 and 9, because that's what a digit is. Now let's revisit these first 2 here, because I'm a little suspicious about what we have going on here. So let's reread the verbiage. The first 2 digits must be your enrollment year. And then the college is choosing one ID number at random to win a scholarship. So it begs the question, how many enrollment years are being included in this particular drawing, right? Do we have just freshmen, just sophomores, just juniors, just seniors, or could it be any one of them? Are we assuming that everybody from this college is attending for 4 years? What's going on there? So what we're going to do to simplify things is we're going to assume, just like high school, that the folks here are attending for 4 years, so that your particular enrollment year may be the one that's chosen, or it might be one of the other 3. So it is locked in. However, altogether here, we have to account for 4 different enrollment years. Or, in a nutshell, 4. These first 2 spaces together are going to act like a 4. Okay, so maybe your enrollment year was, 2017, or it's 18, or it was 19, or it was 20. Okay, those are the first ways that every student ID number at this college is going to start. We had to make that assumption because they left us hanging with that. So what do we get here when we multiply all these numbers together? We get 4 followed by 6 zeros. 1, 2, 3, 4, 5, 6. So that is how many total ID numbers that could be generated. The college is choosing one ID number at random to win a scholarship. Okay, so to answer this question without thinking too much, they're going to generate an ID number, which means one winner out of 4 followed by 6 zeros. So that's 4 million possible ID numbers. Divide 1 by 4 million. 1 divided by 4. 1, 2, 3, 4, 5, 6. And we get 2.5 e to the negative 7, so that's going to be 0.1, 2, 3, 4, 5, 6, 2, 5. There's your probability. Scoot the decimal over twice if you want to convert that to a percent. So 0.12345%. Okay, now that's the answer here. However, again, this question is leaving us assuming a lot of things. Thing number 1, this college is really, really popular. There's 4 million student IDs we're assuming exist. Is this really the case? No. They're not going to be 4 million people going to that college. So our sample space is not that big. But without any additional information, this is the best we can do. So we are going to keep it like that. So, homework assignment is very similar to the previous lessons. We're building on using the fundamental counting principle, which I just used here, and answering questions that also involve using the complement. So, let us know if you have any questions.